Using normalization layers to improve deep learning models. You've probably been told to standardize or normalize inputs to your model to improve performance. But what is normalization, and how can we implement it easily in our deep learning models to improve performance? Normalizing our inputs aims to create a set of features that are on the same scale as each other, which we'll explore more in this article. Also, thinking about it, in neural networks, the output of each layer serves as the inputs into the next layer. So a natural question to ask is, if normalizing inputs to the model helps improve model performance, does standardizing the inputs into each layer help to improve model performance too? The answer most of the time is yes. However, unlike normalizing our inputs to the model as a whole, it is slightly more complicated to normalize the inputs to intermediate layers as the activations are constantly changing. As such, it is infeasible, or at least computationally expensive, to continuously compute statistics over the entire train set, over and over again. In this article, we'll be exploring normalization layers to normalize your inputs to your model, as well as batch normalization, a technique to standardize the inputs into each layer across batches. What is normalization and why is it helpful? Normalizing a set of data transforms the set of data to be on a similar scale. For machine learning models, our goal is usually to recenter and rescale our data such that is between 0 and 1 or -1 and 1, depending on the data itself. One common way to accomplish this is to calculate the mean and the standard deviation on the set of data and transform each sample by subtracting the mean and dividing by the standard deviation, which is good if we assume that the data follows a normal distribution, as this method helps us standardize the data and achieve a standard normal distribution. Normalization can help training of our neural networks as the different features are on a similar scale, which helps to stabilize the gradient descent step, allowing us to use larger learning rates or help models converge faster for a given learning rate. Using normalization layer in TensorFlow. To normalize inputs in TensorFlow, we can use normalization layer in Keras. First, let's define some sample data. Then we initialize our normalization layer. And then to get the mean and standard deviation of the dataset and set our normalization layer to use those parameters, we can call normalization.adapt method on our data. For this case, we used expand dims to add an extra dimension as the normalization layer normalizes along the last dimension by default. Each index in the last dimension gets its own mean and variance parameters computed on the train set, as that is assumed to be the feature dimension, which for RGB images is usually just the different color dimensions. And then to normalize our data, we can call normalization layer on that data as such, which gives the output, and we can verify that this is the expected behavior by running np.mean and np.stead on our original data, which gives us a mean of 2.0 and a standard deviation of 0.8165. What is batch normalization, and why should we use it? From the name, you can probably guess that batch normalization must have something to do with batches during training. Simply put, batch normalization standardizes the input of a layer across a single batch. You might be thinking, why can't we just calculate the mean and variance at a given layer and normalize it that way? The problem comes when we train our model as the parameters change during training. Hence, activations in the intermediate layers are constantly changing, and calculating mean and variance across the entire training set for each iteration would be time-consuming and potentially pointless, since the activations are going to change at each iteration anyway. That's where batch normalization comes in. Batch normalization, under the hood. Now that we've seen how to calculate the normalized activation maps, let's explore how this can be implemented using NumPy arrays. Suppose we had these activation maps with all of them representing a single channel. Then we want to standardize each element in the activation map across all locations and across the different samples. To standardize, we compute their mean and standard deviation using which outputs. Then we can standardize an activation map by doing, and these store the outputs. But we hit a snag when it comes to inference time. What if we don't have batches of examples at inference time, and even if we did, it would still be preferable if the output is computed from the input deterministically. So we need to calculate a fixed set of parameters to be used at inference time. For this purpose, we store a moving average for the means and variances instead, which we use at inference time to compute the outputs of the layers. However, another problem with simply standardizing the inputs to a model in this way also changes the representational ability of the layers. One example brought up in the batch normalization paper was the sigmoid nonlinear function, where normalizing the inputs would constrain it to the linear regime of the sigmoid function. To address this, another linear layer is added to scale and recenter the values, along with two trainable parameters to learn the appropriate scale and center that should be used. Implementing batch normalization in TensorFlow. Now that we understand what goes on with batch normalization under the hood, let's see how we can use Keras's batch normalization layer as part of our deep learning models. To implement batch normalization as part of our deep learning models in TensorFlow, we can use the keras.layers.batch normalization layer. Using the NumPy arrays from our previous example, we can implement the batch normalization on them, which gives us the output. By default, the batch normalization layer uses a scale of 1 and center of 0 for the linear layer. Hence, these values are similar to the values that we computed earlier using NumPy functions. Normalization and batch normalization in action. Now that we've seen how to implement the normalization and batch normalization layers in TensorFlow, let's explore a LeNet-5 model that uses the normalization and batch normalization layers, as well as compare it to a model that does not use either of these layers. First, let's get our dataset. We'll use CFAR10 for this example. Using a LeNet-5 model with ReLU activation, training the model gives us the output. Next, let's take a look at what happens if we added normalization and batch normalization layers. We usually add layer normalization, amending our LeNet-5 model and running the training again, this time with the normalization layer added. And we see that the model converges faster and gets a higher validation accuracy. Some caution when using batch normalization. It's generally not advised to use batch normalization together with dropout, as batch normalization has a regularizing effect. Also, too small batch sizes might be an issue for batch normalization, as the quality of the statistics, mean and variance, calculated is affected by the batch size, and very small batch sizes could lead to issues, with the extreme case being one sample, have all activations as 0 if looking at simple neural networks. Consider using layer normalization, more resources in further reading section below if you're considering using small batch sizes.